All right, so I'm going to do this a bit out of order. So I'm doing lecture 9 about hashing before lecture 8, which will be about memoization. Um, so the hashing, if you're probably already familiar with at some degree, which is essentially just at the base, definition of a hash function is taking, say, some data and then passing it through a function, and then on the other side of that function you receive some form of encoding. And I think that more generally speaking, hashing it really kind of expects that sort of data on the one side to be arbitrary, so it could be a string or even an image or even a value. It doesn't really matter what we're hashing, because then what some kind of function then applies to it and then breaks it down to some output, which is generally an integer type of representation. Because the purpose of a hash function, as we'll go into in this lecture, is to allow us to sort of organize data in sort of an associative way. And what do I mean by associative? Well, let's kind of dive into it. So what are also known as associative arrays are also known as dictionaries or maps. And essentially, if you can, we all have been pretty comfortable up until this point with static arrays, right? So ints and characters and longs, where you have a long contiguous memory block, and that memory block essentially is split up into the sides of those individual components. And so you have, longs after longs, ints after ints. And anyways, as we've discussed in our previous lectures about sort of the architecture of the computer and the way that our memory interacts with our cache and then our CPU, these are actually very, very optimal ways to organize our data, because, more often than not, when I look at, the int at the fifth position, I'm most likely going to look at the integer at the sixth position very shortly after, very likely. And so our caches are built and designed in this way to accommodate the likelihood that if I'm looking at this piece of data in this array, I'm very likely to look at the piece of data right next to it as well. Now, for better or for worse, most of the data in the world does not come in these contiguous blocks, right? When you're standing in line, or when you open up a lemonade stand, the person that comes to you now versus the person that comes to you later, they're unrelated. Generally speaking, things are kind of eventful in life and in computing and in the types of systems that we like to design. Those kinds of eventful occurrences don't necessarily line up with our perfect memory model of hoping that things are contiguous. And if we are really kind of thinking about, performance, then we can maybe hack this and try to create associations between events such that likely events and likely data that's next to each other should be kind of organized in this way. But we also want to do that in a way that is very, very fundamentally aligned with the way that our memory functions as well. And so, long philosophical spiel about why we have associative arrays. So ultimately, an associative array, dictionary, or map allows you to key into your array. So before, we were keying into an array with an integer, right? So I want the fifth or the seventh or the 20th element in that array. So I literally just go, array bracket 5 bracket, and then that tells the compiler I want to look at the fifth position in that memory sequence. But what if we don't use an integer? What if we wanted to use, say, a string? So the trivial example of this is, say, I want to look up my user ID. I have a username, but that correlates to a user ID that the system actually uses, because parsing a string every single time would be very inefficient. So I have a user ID that's unique to me, but I want to look it up based on my username. This is a very common, sort of very basic thing. And so what I want is I want to be able to go array bracket Idan, right? Idan's my username. And then to be given back what is a very large number, potentially a an array in its own right. And so how do we do that? Well, we would have to associate my name with some lookup that would then be able to tell the array to look in this particular location in memory. And that's exactly what a hash function does. And so when we talk about dictionaries or maps, that's essentially what we're doing, right? A dictionary is kind of a nice mental model to think about, right? Because what we're using very often is a word. The strings are a pretty common kind of scenario for hash tables, although again, you can use any kind of thing to key if you'd like, as long as the hash function you're using is defined for that particular kind of data. But a dictionary is literally this, where if I want to look up the meaning of a word in a dictionary, I would use that word based on its ordering in the alphabet if I had like a physical dictionary, and I'd go to the page and eventually kind of get to where it's going. So like we are, as people, are doing this because if you think about words, right, tomato and apple, as far as words, as far as the organization of the letters, have nothing to do with each other, yet mean something similar. So again, it's about associations, and these hash functions, while don't necessarily work in the association level of, how we think as human beings, they do mathematically, and I think that that's the way that that's kind of the goal. So this hash function, essentially an associative array operates on these sort of abstract data types, which include a key and a value pair. And the idea and the hope is that the key appears at most once, but as we'll know, that's not necessarily realistic sometimes. So, oh, cool, this is always popping up on me. So hashing. So how we accomplish this is through what's called a hash function. And what this allows us to do is basically find this location in the array of memory, and quickly insert new elements into the array to retrieve existing ones, as well as to find them to be removed. Now, there's downsides, there's pros and cons. Sometimes these operations can be slow, and we'll talk about why that may be. And searching for say I'm trying to look for a specific user ID without the knowledge of the respective username, right? So now I have to search for every single one. Well, that's pretty slow too. So this does not give us ordering. The association now breaks in certain ways where, say, we want to associate against username, but not necessarily, that might not help us so much in terms of associating against the actual values that those usernames relate to. So yeah, that's the difficult part. In fact, it doesn't even help us so much with, knowing what the usernames are respective to these values. So it's not like I could even alphabetize the usernames. This is, by the way, a very common, like this is the way a lot of password systems are used, right? Where the password is not saved on the website or on the server. What happens is, so you're like, hey, user, what do you want your new password to be? And I say blah 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 blah, and then the server takes the blah 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 and adds what's called a salt value. So some kind of thing that only the server knows, some secret piece of string, usually a pretty complex one. And so it becomes blah 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 blah, and then concatenated like, your mom or something. And so blah 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 your mom then gets hashed, and that value of the hash then gets saved. And so then every time I enter my password, the website doesn't actually know what my password is. The website can only know if the password I provided it plus that salt value that it does know combined, then hashed, is equivalent to the hash value that is associated with my password, with my username. So again, that in this way, the server and this application and this company can kind of have plausible deniability, like we don't actually know what your password is. And so but now you have this other kind of failing point of, well, if somebody gets access to, one value, one hash function or hash value, right? And they can kind of work that against a bunch of known passwords, yada yada yada. There are brute force ways to ultimately figure out what that secret is, and then potentially break into a lot of people's accounts. So nothing's perfect. Cool. So here's the problem. We want to store a collection of data. We want to add to it. We want to delete from it. We want to search it. using this information in this form of key value pairs. So how might we do this? Well, I mean, we just talked about how we might do it. Another version of this problem is, like I was mentioning, you want to keep track of students and their IDs. So this is the exact example of like my username and my ID. But say in this case, we want to do it by keyed on name. So the type of the ID here is range from 0 to 99. So this is relatively easy. And yeah, the ID number becomes a oh, I see. So sorry, I've got this backwards. We're basically trying to look up user information. So your name, your particular details using an ID. So you're given an ID and you can use this to key and figure out what that is. And it's a sparse data set because say we only have 30 students and 100 potential IDs, so not everybody's going to be contiguous. And that way we can kind of use this ID value to look up your respective name, your class schedule, whatever. So if we have a very small array, however, so we have 100 IDs, okay, so now we've constrained it down. We only have 10 students potentially because we only have, a small array. Suppose, how would we then turn 100 values into only 10? Right? What kind of function could we use? We need a function that essentially takes that value of 0 to 100 and then maps it to a value of 0 to 9. So this function, even a trivial one such as this, is what's called a hash function. And a pretty common example of this type of hash function is just the modulo operator, which will then take, say I have, 100 values, and I take that value and I mod it by 10, I'm guaranteed to the output of that to be between 0 and 9. Now, the problem with this approach is probably pretty obvious. Say my ID is 99 and somebody else's ID is 89. Well, what happens then? But we'll talk about that in a minute. So essentially, we are taking that value and you're using that hash function to essentially represent a location into an array that may not be directly related to, it's related, but it's not directly the value of that initial index. So whatever value I provide this hash function, it will then, map to a particular place in this memory. So what's nice about this is now if I have my ID, I can get directly to the data. So I no longer need to know that it's located in memory location number 7 because I know my ID and I can give it 77 and it will give me that correct value. Now, there's a lot of different ways to do this, right? For example, in the hash ID, which is kind of what we did already, we could use the first number, so the first digit, right? And that's what we kind of accomplished using the modulo function. We want to potentially use a hash function that uniformly distributes keys throughout the array. This is what's called uniform hashing or bucketing, right? Where it's almost like a histogram, right? Where values between this and this and this and that get placed into different parts of the array, or what are called bins or binning. There's a lot of funny names for this thing. If we use a division hash function, like a remainder of a division, so like a modulo operator, what we really want is we want kind of a prime number in the form of 4k plus 3, where k is the number of buckets. Let me think about this because I haven't thought about that before. Okay, sorry, I had to take a moment to really absorb this a little bit. But essentially, the 4k plus 3 is just a form of a prime number. And just generally speaking, when you're talking about division type of hashing functions, you really do want to choose a prime number. And the 4k plus 3 form, it's proven that there's an infinite number of these, primes in this form. And the proof is kind of outside of the scope of this class, but still, the reasoning for this is has to do really with the density and kind of observed density of hash functions in general. So it's a bit of an empirical result, although I think it's mathematically provable, again outside of the scope of this class. But yeah, generally speaking, the way you would do this to get to that 4k plus 3 number is you would kind of define the number of buckets that you would have, and that's essentially the size of your array, or the size of your hash function. So say it's 10. So in this case, what we would do is we'd go, okay, 4 times 10 is 40, plus 3 is 43. Is that a prime number? If it is, which is 43 a prime number? I think it is, so great. But say we chose 11, which would give us, 44, and that's not a prime number clearly because it's even. And so you would then find the next larger prime number that fits this form above that. So you keep on going up k until you hit a prime number. And that allows you to really avoid collisions kind of optimally, or close to it. So because there's no optimum in this stuff with regards to avoiding collisions, because that's really a function of the kind of data that you're putting into your hash function, right? So say we are doing the previous example of like 100 IDs for only 10 locations, and we have a hash table, of 10, or in this case 43, right? So now we're doing 100 to modulo 43, which kind of expands and reduces the likelihood of our collisions. Well, you're guaranteed a likelihood if you have more than 43 students, right? So, or you're really guaranteed a likelihood. Say our hash function is, modulo 43, right? So we're definitely guaranteed a collision if we essentially go 0, 43, 1, 44 for whatever reason. So keep that in mind. But however, you can kind of see just with that example, in the case of 43 over a span of 100, we essentially can't really get much more than 3 collisions, and only for a very small portion of that. And you can even argue, say, like, well, why not use 50 then, and so on. So you can kind of see there's a lot of kind of trade-offs here, and what is actually done in practice we'll get into, and how this is handled essentially in actual practical hash tables. So yeah, but anyways, there's a lot of hash functions, and some of them get really complicated, and again, kind of beyond the scope of this course, but some of them, a lot of them are active research subjects, especially for securities, because as I mentioned, hashing, as much as it's very useful for storage of data and access and retrieval and so on, has a lot of impact with regards to security and the ability to sort of secure and encrypt data, which is really critical. So we've already talked about collisions a bit already, but like, what could go wrong? Obviously, we could have a hash function of a key result in the same value. Because you might want to add, so say you want to add a value to an array, and the array is just a simple, all we're doing is it's just, okay, I'm running a hash function and I'm accessing that part of the array, but perhaps it's already in use. And if we do this, we're just going to overwrite the data that's in there, and we'll never know. And that's what's called a collision. And so if there are no collisions in a hash table, what would be the complexity time, the time complexity of that? I'll let you think for a moment before I answer. Right, so if there are no collisions, our complexity is essentially n, right? Because if we have no collisions, then I'm sorry, it's not n, it's 1. I'm sorry. You pass the thing, you get the 1. That's it. That's the strength of the hash table, is that the time complexity is essentially constant, right? It's just the time of lookup and running that hash function, and really most of our both even insertion, even deletion, even retrieval are all O1 complexity, as long as we don't have any collisions. Because if we have collisions, clearly, unless we don't care about collisions, which is sometimes true, but most of the times it's not, if we do care about collisions, the complexity then becomes more complicated because we have to do something. So how do we handle collisions? Well, there's a number of different ways to deal with collisions, right? For example, linear probing is one of the more effective and I think more most efficient algorithms to do this. And what we do is to handle a collision, we essentially just put our data in the next open spot in our array. Now, this can present potentially a different collision, right? Because then we can, you know, like that value of the next spot is a hash function for a different key, right? But however, the really beneficial thing about linear probing is if we put it just into the next spot, then ultimately our cache coherency is very good. Because again, talking about kind of the way that associative arrays are trying to, define and work against the world, events that happen like that are, close, may happen like that closely all the time. And so being able to sort of figure out where those are is good. Now, how would you find an object in a hash table that uses linear probing? And this is kind of the tricky bit about it, right? Because if the object that you're looking for has the exact same hash function, then you do need to find a way to sort of differentiate between the two, ultimately. And so you would have to know that there are multiple values that are in that location, and similarly, you would also have to do that with, the delete case. One moment, I want to confirm something. Okay, sorry. So I wanted to kind of clarify a little bit deeper on this linear probing, these two cases of insertion, as well as retrieval and deletion in a linear probing case. And so one thing that if you're doing linear probing again, which is basically we're going to add it to the next available spot, and we're going to create these kind of contiguous runs. So say where we have like 3 collisions on the kind of hashed value of 1, we're going to have 3 different things in that row. But this is kind of the important thing, like how can you differentiate between them if we're trying to retrieve them? If I say, okay, say my name Idan and the name Bob, both correlate to the value of 1, and then I say, okay, well I put in Bob and I get the hash function 1, well how does it know which one to give me? So you do need to save the respective key in the linear probing context. And per what I was saying about like passwords and things like that, obviously that's a no-no. And so you do have to kind of think about that with regards to the approach that you take here, because ultimately the entire value, while it's going to take up a lot less memory overall, right? Because you can imagine our value space is much smaller than our hash space. So our value space could be infinite, right? Whereas our hash space is only a few hundred values. But the memory does need to include some version or some more kind of unique version of that name, such that there is no collision in the key. That way, I know what I'm talking about. And as you can hear as I'm saying, potentially you can even hash it again with a different function or a variety of functions until you can ensure that there is no collision between that, or come up with a bunch of other ways. And deletion kind of works the same way, right? You have to find the correct key to delete in the sort of collision set. Now, deletion brings up another edge case that's really important to think about, which is, well, we're kind of creating these contiguous runs, and in some cases, that run will hit another key that may be used. So say, Idan, Bob, and Stacy, are all keyed against 1. So now I have 1, 2, and 3 filled up by Idan, Bob, and Stacy. But then I have another value, which is, say, Jim, and Jim technically should be keyed on 3. And so now Jim has to go into 4 because 3 is taken up by Stacy. But then say we delete Stacy. So Stacy's now out of the table, and now 3 has been made available. But Jim is in number 4. So now we've got another problem. We have a empty space where Jim should be, but was not because of that collision. So what do? Well, we actually have to rehash in that scenario. So sometimes when you delete, you do have to kind of reevaluate the hash table and sort of figure out, oh, well, we've created this empty space and we have to move things around. And that may create empty spaces. And so on and on and on and on. And so deletion with linear probing can become a lot more time complex than the insertion case or the retrieval case. And as you can hear in the insertion case and the retrieval case, is also a very high likelihood that we're going to have to sort of iterate a little bit if there is a collision, and we'll get to kind of the factors that determine that in a moment. Up, always. So linear probing, as you can hear, the performance can be bad, especially if you're deleting a lot. However, it's extremely easy to implement. And the other nice thing about this, and the sound that is like, why would this be nice? Well, as the hash table gets fuller and fuller, you're going to have larger and larger consecutive stretches of the array. And this is what's called clustering. So as I mentioned, as we start to kind of lump things around, you kind of overlap in these different keys, and all of a sudden things are taking up space, and they kind of cluster and stick together and stuff like that. But that's actually a good thing for our cache coherency, right? For our we're less likely, especially if this is the data that we're going to be using all the time. Clustering is actually a good behavior for our cache behavior and our memory. The likelihood of trying to access data that's not in our memory currently, in our cache currently. So another approach, and we kind of already hit on this a little bit, is just hashing again. So if we have a collision, then we hash again. And this is actually a pretty simple approach, right? So if I hit a collision, and you can, again, you might have to store the original key just to kind of because say the original, and you might also have to bubble things up as well. But say I put in Idan and then I put in Jim, and we're both keyed to 1 with one hash function. Well, I'm going to key Jim with a secondary hash function. So now when I retrieve and I with Jim and it hits Idan, and there's again, I have to save my key. I have to make sure that I'm at the right key, and I didn't find it, so I just hash Jim again with the secondary hash function. And you can rinse repeat for as many times as you want, so you can double or triple or so on. But again, now you really have to kind of consider that situation of when I remove Idan and Jim is somewhere else, right? And now if I single hash Jim, it'll go to that empty cell, and then the array will tell me there's no Jim here. So in that case, when you delete Idan, you have to make sure that any double hashed values, and you essentially have to rehash the table, which can be ON complexity, right? So kind of have to think about that as well. Another way to do this, instead of dealing with any of that stuff, we can essentially treat the array as an array of arrays, or an array of lists, or an array of vectors, or whatever. This is actually a pretty common approach, especially if you know you can kind of preempt this and say, well, we expect X number of entries in every single one of these buckets. And this can be very efficient if you know that, right? If you know, for example, in our case, we have 100 elements, but only 100 IDs and only 43 locations in the array. We have a pretty high likelihood. So if every single element had 3 locations, then we will be fine. However, like at that point, why not just have an array of 100 values? So it's a trade-off, right? You kind of have to know what you're doing, but it is a good way to sort of deal with data if memory is not what you're worried about, and the hash function is really this association of key to, of data to value, like just the ability to turn a string into an integer lookup, as you can imagine, is very, very valuable for programming, right? Or just building an interesting architecture. So sometimes you will make an associative array for no other reason than a lookup approach. And in that sense, the memory doesn't matter. So you can ensure that, and if you know all of your potential inputs, right, you can design it in such a way that you'll never have a collision, or collisions will be predicted because you have sufficient memory to. So the list, each element of the array, instead of being um, a just individual location, can be a list, an additional or dynamic array, or a vector, right, which is a resizable static array. So yeah, this is chained hashing is also kind of a catch-all type of thing. So here's a very kind of simple hash function, but this is pretty representative of most hash functions. It's sort of pretty common to do this on strings. As you can hear, strings are probably the most common type of data that we're hashing. So we start off with a hash value of 0, and what we do is we take we convert our string into a character array, and for every character in the array, we're essentially just adding the value of that character and like the ASCII value to this hash value, right? And then it goes up and up and up and up, and eventually we modulo that to ensure that it's within a certain bound. And so the return value of this function will be kind of randomized in the space to some degree. Again, like proving the distributions of these hash functions is very much outside the scope of what we're talking about here. But you can kind of see how these hash functions are a little bit of craft. You can kind of come up with different ones if you'd like. There are very standard ones, and they're very secure ones with different properties, and it goes into deep into the mathematics justification of them. But ultimately, even something like this will work most of the time. And that's, I think, the key here is that you don't need to have perfect in hash function land. You just need to have most of the time, right? And if it's not good enough, you'll know very quickly, right? So in this case, size is an externally defined variable. In this case, it was, say, size is equal to 100, and now we can essentially map any string to the 100 values of our hash table. So the let's research a bit of hash functions, and I will kind of talk about these once you have a chance to do it. So feel free to pause the video after I talk about it. But what is the hash function that Visual Studio uses? As you can, in C#, there's actually a you can hash any object. You can basically pass an object and get a hash for it. So like, what is that? What do you think that function looks like? What is the default size of the hash table in C#? And let's look up a couple of hash functions. Like, could we implement one, and does it work well? I'll take a moment. Okay, so you might be surprised to hear, but one of the most common hash functions is to simply pass back the value of the pointer, or the memory location of the object in Visual Studio. Because that's good enough, right? Ultimately, most of our computer systems are going to be limited largely by the ability to reference memory. And that in and of itself is something that we have to consider, right? There are many more things in the world, in the universe, than what we can represent with an integer. For dealing with billions of lines of data, we only have a 16-bit value to reference them. And again, so more often than not, the hash value that you get in Visual Studio is kind of naive and returns you the value. Now sometimes you have to combine it, and you can sort of do different things, like you can add them, and then like we did before, or you can essentially do an exclusive OR. So kind of talking about some of alternative hash functions. You just kind of get creative, and you take your data, the internal representation of your data. Say you have a point, you want to hash a 3-dimensional point. Well, what you can do is you could exclusive OR all 3 values of the point, say in floating point representation, and that is your hash function. Does it work well? Well, it depends on your implementation, right? If it really comes down to the fact that you have to sort of understand the mathematical implications of, say we have a bunch of very densely located points, will that XOR operation work well? Obviously, an addition won't work well if we have a bunch of values that are very close to each other. An addition is not going to give a substantial distance from each other because they're all very close together. So an exclusive OR of the floating point representation may be really good for that, because even though the values are very close, dimensionally, the values may be very different because, 0.0, as we learned about floating point representations, 0.03 and 0.04 have very different binary representations, and so an exclusive OR, especially against the three different dimensions, may result in some very different hash values. But if we just add them, they're very likely going to be kind of very near each other, and that might not be a good thing. However, if you've got points that are very sparse and very, very far away from each other, the exclusive OR may not work very well because the values may be very similarly different, meaning in the exponents or in the sign or something like that, right? Whereas if you add them, the hash function would be better. So I think that it's really a matter of understanding your problem space and understanding how to apply that problem space to a hash function that then gives you the right kind of, call it, distribution that you're looking for. With regards to the second question, what is the default size of the hash table in a dictionary in C#? Well, you'd be surprised, and maybe not, it's 0. C# actually uses a very sort of conservative approach in most things like this. And when you create a dictionary, much like a vector, it will start off with a size of 0. When you add to it, then it will sort of make it bigger and rehash the entire thing, which is nothing when it's 0. So it doesn't cost it anything to rehash when you're initially creating and initializing this object. And then every time you add to it, as soon as it gets to sort of too full, it may make itself bigger, and you can set that value, which we'll talk about in a bit, because that's determined by what's called the load factor of the dictionary. So getting a hash value, each object in C# has a get hash code method. As I mentioned, there is a default implementation, but most often when this is important to developers, you override this particular method. This will return a value that can then be used with a hash table, and the hash table being the C# hash table object. And as we kind of already know about hash functions in general, this value may not necessarily be unique. So if you're worried about your implementation conflicting, right? Say we're doing a lot of this stuff, and you think that the default version of this will not be sufficient for your hashing needs, such as you have a very small hash table, and you want to maintain a very small set, you should override this method and then hinge it against the internal representation of your object, because the default get hash code method does not understand what your object is doing or what it's made up of, and is most likely going to give you a very kind of naive hash value. So let's talk a little bit about load factor, because I think that's already now come up a little bit in that this is something that many dictionaries or associative arrays have to use because, as you'll see, the load factor, which is also just the sort of ratio of how much of our hash table memory is used up, is a very important thing in terms of performance, and then the sort of resulting time complexity that we're going to suffer for particularly insertion, deletion, and retrieval. And so in this case, alpha is used to represent the load factor, and this is based on like Donald Knuth's Art of Programming, which I really recommend buying that and slowly going through it. It's his life's work. And a lot of the stuff that we're learning in this lecture is based on that 1962 book that he wrote about this in one of the volumes of the Art of Programming. There are 5, I think. Anyways, so alpha, the load factor, is equivalent to the number of elements in a table divided by the size of the table. So that's essentially just what's the percentage of memory that we're using. So I'll let you take a moment to think about what these questions are. What does a load factor of 1 mean? What is a load factor of 3? Which would be better? And what do you think would be a good ratio? So I'll let you think about that before I answer them. Cool. So, I'm assuming you paused the video when I say that. If you haven't in the past, you should do so now. Okay, now I'm going to answer. So, what does a load factor of 1 mean? Well, obviously the number of elements in the table is equal to the number of the size of the array. So we're effectively fully loaded. To add another element means that we're going to have to be, we're guaranteed a collision. What does a load factor of 3 mean? Well, that means that the table's size is 3 times smaller than the number of elements in the table. This means that we have basically, at minimum, collided, on average, I suppose, have 3 collisions per location, right? In theory, we could have just like one location that's like, bleh, huge, but in short, we have many more elements in the table. And you'll be like, wait a minute, but you just said that it's how much are we utilizing the memory? Well, I guess to be more explicit here, it's about the size of the table array. And as we talked about, there are many ways to deal with collisions. So this would obviously not work with linear probing, and it wouldn't really work with double hashing either. So in this case, we're most likely using chaining or some kind of list or something like that to deal with collisions. And so in this case, 3 would be possible. So which one of these would be better? Well, clearly we would want 1 because right now, like every time we add an element to a hash table of load 3, we are essentially guaranteed to at least 3 times most likely potentially a minimum 3 times, or I don't know, minimum whatever, but like average 3 times have to kind of like poke around. Whereas with 1, we're guaranteed maybe 1 collision, but that's less than on average 3 collisions. And then what is considered a good ratio? Well, clearly the good ratio is less than 1 and probably closer to half. Or even 0.75 may be kind of the breaking point because, and I think that this is also kind of a problem-dependent question, right? Because say your load factor is 0.25, but for whatever reason, the way you've designed your problem, you're essentially getting a collision every single time, so a load value of 0.25 is bad, or the way the hash function you're using is bad. You kind of can look at it 2 different ways. So, if we're using linear probing, and in a non-full hash table with no removals, and using uniform hashing, which we've talked about before, where the hash function is sort of uniform throughout the values of the hash table, the average number of elements that we have to examine to get to a successful search is this value of 1/2 times 1 plus 1 over 1 minus the load value. And so this is kind of the average between 1 and the likelihood, essentially, of having a collision, which is 1 over 1 minus alpha. Because say alpha is 0 in this case, then we're going to have 1 plus 1 divided by 2, which is 2. Say our load value is going to be 0.5, right? So our 1 over 1 minus 0.5, which is 0.5, which is 2, so it's like 1 plus 2 divided by 2, which is 1.5. And so you can kind of see how this equation, as you get closer and closer to an alpha of 1, goes closer and closer to infinity. So if our load value starts to get closer to 1, we are guaranteed essentially a collision very, very quickly. And on top of that, if we're doing linear probing, as I mentioned in this previous thing, a load factor of greater than 1 is legitimately not possible with linear probing because you are now, on average, going to have to go through an infinite number of elements, unless you're using chaining, as I mentioned. So alpha over 1 is not possible for either linear probing or double hashing, because double hashing is still operating on the same array. Now, if you do double hashing with a separate array, well, that's a different story, right? And that's technically chaining. If you know, just a more fancy version of chaining. Searching with double hashing, again, right, is in a non-full hash table, no removals, using uniform hashing. The average number of table elements examined in a successful search is negative logarithm of 1 minus alpha, the natural log of 1 minus alpha. And the negative is because, because we're sub the value of e, this is, we're essentially going to infinity, but we're going negative infinity. If you know the curve, the logarithmic curve kind of goes down here and up. So we're looking at this portion of the curve that's going down is asymptotically to infinity, and so we kind of reverting that, and we're going to be going, if you look at the curve, as we'll see in a second, we'll go very, very close to infinity, and eventually it'll be impossible again. So in this case, with double hashing, as I mentioned, as alpha gets closer and closer to 1, we're getting closer and closer to an infinite number of elements that we have to seek out, and then divided by an additional, thing. So yeah, well, not divided actually. We go to infinity, the bottom turns into 1. Um, and so I guess when alpha is equal to 0 in this case, it's defined as 0. Because that's mathematically, maybe you'd look at the limit here, but okay. So yeah, as you can see, as our load goes closer and closer to 1 with double hashing, things get much, much more difficult. So here's just a quick example. I pulled this from a really great deck from this Tel Aviv University. And you can just sort of on the left see the variety of things. I know we didn't talk about all of these equations, but as you can see with linear probing, that equation in a successful search, I know we didn't talk about you know, the other values, but as you can see, right, and here, as we get closer to a load of 1, the average number of, you know, things, the elements that we have to go through is going closer and closer to infinity. And that's pretty painful, right? One thing I'll, you know, point out, right, so with uniform probing, that we were talking about in the beginning, even though uniform probing, and by the way, uniform probing, the difference between linear probing and uniform probing is that we don't do what we were talking about with linear probing. We just put it where it should be, and if there's a collision, we give up, or we have to do chaining and so on. Let me just confirm that. I don't want to mislead you guys. Okay, I'm sorry. Let me kind of double back on uniform probing. Just to, not that this is actually part of like in scope of this lecture, but just so you understand. So uniform probing does not give up when it doesn't find a collision. It just simply increments. And we didn't cover this in this lecture, but that's okay. But we basically modulate the hash function by adding 1 to it, or kind of checking each incremental bit of it. So we sort of somehow keep looking. We keep hashing until we hit an available location in the table. It doesn't matter. You don't need to know too much about that. We didn't go into uniform probing versus linear probing. With linear probing, we just iterate down the array until we find an empty spot, as we talked about in this lecture. But one thing I do want to bring up here, while uniform probing, you can see is much more efficient, right? Because this curve over here is going to, as you go closer and closer to full load, you know, it goes to 1, only asymptotically, very kind of far in the end. And the reason for that is because it's in a way like we're kind of double hashing. It's not quite double hashing. We're not hashing it with a different function. We're not hashing it again. What we're doing is we're changing the value such that we're looking for a different location in our hash table. And so it's very, very good at utilizing all of the space inside of our hash table much more efficiently than even linear probing, which you can see starts to grow much quicker, and that's kind of interesting to kind of note. However, like we mentioned in the beginning of the lecture, one of the really beneficial aspects of linear probing, in particular compared to uniform probing, is that clustering. Because as I just mentioned, you know, a good hash function, 2 values will produce very divergent values on the other side of the hash function in the hash space. And that's not what we want for good memory synchronization, memory coherency, right? If we want to have, we really want to have a hash function where the two, like say it's, you know, Idan and Jim, we want those two to be 1 and 2. That's like an ideal, right? Because if we somehow we can know what our inputs are going to be and the order they're going to be, that's the way we want to order our data. However, that's impossible. Maybe some machine learning techniques are starting to be able to figure that out, but trust me that those algorithms are much more complicated than a hash function. And so, you know, it's interesting to note that here are the trade-offs right here in this graph, where uniform probing, while massively inefficient from a computer architecture standpoint, is much more efficient in terms of a memory utilization and kind of spatial context. whereas linear probing is less, less efficient time complexity, but much more efficient in terms of the memory architecture of our system. And I won't go into the unsuccessful search here, but if you're kind of interested in looking at it, as we get closer to the load factor of 1, an unsuccessful search will eventually fail, because we're going to have to look at like infinite number of things to know that it's not in our array. And similarly, we see that much quicker. So an unsuccessful search in linear probing very quickly goes to large numbers, even at a very low load factor. And so if you take a look at these numbers, which are not starting at 0, so you can see 0.5, everybody's pretty well behaved still. And at around 0.7, we start to see that linear probing starts to kind of take off in the unsuccessful case. So yeah, you can kind of see very well in this graph the variety of kind of trade-offs that we're looking at with regards to at least linear and uniform probing. Cool. So with regards to chained hashing in a non-full hash table, this is one that was not in that previous one. And remember, chained is when we just kind of create these like lists or arrays for each element that has a collision. We basically take that likelihood divided by 2 plus 1. So we're guaranteed to check 1, right? And then we have that likelihood divided by 2. And that's the average number of table elements that we're going to have to search. So you can see this is not bound by, so as alpha gets to over, you can actually have an alpha over 1, as we talked about. And so here, this is actually like some empirical data, and this is the last slide in the lecture. You can see that as the load factor goes up, linear probing eventually is impossible, as double hashing is, and chained hashing actually, you can see, is relatively linear in its increase with load, and is pretty good, right? But keep in mind, right, it's eating a lot more memory, and it's kind of failing in other ways. And whereas here, linear probing and double hashing, even at load factors of 0.5, they're all relatively similar. And double hashing seems to kind of, chain hashing wins the day simply by virtue of the fact that these arrays that are subarrays are not very hard, right? Like the complexity of going through the chain is quite low. And so, and this particular graph, right, definitely does kind of reflect a lot of what I've been sort of hinting at this entire lecture, which is you really need to, if you have a very specific use case, why you're using linear probing and double hashing, do it. But chain hashing, unless you have some memory concerns, can really beat these things most of the time. It's a lot of kind of, but you need to understand the different sort of levers you have to pull here. And yeah, and that's it for hashing. And hopefully now you know a little bit more about hash tables and how they function.